In our previous lesson, we introduced the Fourier Series synthesis equation. X of t equals a0 plus the sum of an cosine n omega 0t plus bn sine n omega 0t. We saw that any periodic signal can be built from harmonically related sinusoids. But how do we actually find these coefficients? Today, we derive the analysis equations. Here are the Fourier series analysis equations. The DC component a0 equals 1 over t times the integral of x of t over one full period. For the cosine coefficients, ak equals 2 over t times the integral of x of t times cosine of k omega 0t. For the sine coefficients, bk equals 2 over t times the integral of x of t times sine of k omega 0t. These integrals exploit the orthogonality of sinusoids. When you multiply a signal by a specific harmonic and integrate, only that harmonic's contribution survives. We can also write the Fourier series using complex exponentials. The synthesis equation becomes x of t equals the sum from k equals minus infinity to infinity of xk times e to the jk omega 0 t. The analysis equation is xk equals 1 over t times the integral of x of t times e to the minus jk omega 0 t. The complex coefficient xk encodes both amplitude and phase. The relationship is xk equals 1/2 times ak minus jbk for k not equal to 0, and x0 equals a0. This complex form is more compact and widely used in engineering. Let's apply these formulas to a concrete example. Consider a signal whose one period consists of two impulses, delta of t plus 1 plus delta of t minus 1, with fundamental period t equals 8. This periodic signal has impulses at t equals plus and minus 1, repeating every 8 seconds. Since the signal is symmetric about t equals 0, it is an even function. Let's compute its Fourier coefficients. Starting with a 0, we integrate the signal over one period and divide by t. Applying the shifting property of the delta function, a 0 equals 1/8 times 2, which gives 1/4. For a k, we integrate x of t times cosine k omega 0t. The shifting property extracts the cosine values at t equals minus 1 and t equals plus 1. Since cosine is even, both terms contribute equally, giving a k equals 1/2 times cosine of k times 2 pi over 8. For bk, the sine terms cancel because the signal is even, giving bk equals 0 for all k. This is a general rule. Even signals have zero sine coefficients. Now, let's visualize these coefficients. Plotting a k versus k, we see a cosine-shaped envelope. The DC component, a 0, equals 1/4. The coefficients decrease and oscillate as k increases. This plot is called the amplitude spectrum. It tells us how much of each harmonic frequency is present in our signal. In the complex form, xk equals 1/4 times cosine of k pi over 4, which gives identical results. In this lesson, we derived the Fourier series analysis equations for finding coefficients from a periodic signal. We learned the trigonometric form with the k and bk integrals and the compact complex exponential form with xk. We applied these formulas to compute the coefficients of a periodic impulse signal. Key insight: even signals have 0 bk coefficients, and the amplitude spectrum reveals the frequency content of any periodic signal. This completes our introduction to Fourier series analysis.